Terrific. Chapter 5, section 5, number 41, and we're dealing with tan inverse of tangent of pi fourths.
I think that one's 39 actually. The one with
Okay, I copied it wrong. Okay. Tan inverse of tan of 2 pi. There we go. Thank you for catching that. I would have gone through the whole thing and then be like, oh, that's the wrong one. Okay. Okay, let's see if we can deal with this guy. Tan inverse of tangent of, and then we have our 2 pi thirds. Okay, so let's do a rough sketch of tangent. So tangent, well, first of all, note that this is in degrees. Maybe it might be a little more easy to see if we do this, divided by pi, right? Then the pi's cancel. So really we have, I guess 3 goes into this 60 times. So really we have 120 degrees. Okay, now note that like a rough sketch of the tangent graph looks like this. We have tangent, well, let's put it in blue. Tangent comes up and goes like that, and goes like that, goes like that, right? And then there's these asymptotes, that way and that way. And the asymptotes are located at pi over 2, which is 90 degrees, and negative pi over 2, which is negative 90 degrees. Right? And that's because, going back to tangent of theta is sine of theta over cosine of theta. And so wherever cosine is 0, it's undefined. And cosine of 90 degrees is 0, so it's undefined there. Right? Of course, it's periodic, so there's going to be another vertical asymptote over here at the next place that cosine is undefined, and it's undefined at 1.5 pi's. So this one's going to be undefined at 3 pi over 2, which is equal to 270 degrees. Good. And then over there, it repeats itself. And then over here, it'll repeat itself, and then it'll repeat itself. Okay, everyone's with me? I'll assume the silence means yes. Okay, so where is 270 degrees? Well, the period of a tangent function, this period right here, from there to there, is pi, or 180 degrees, right? This period. That means that this one here is also same thing. It's pi. Okay. So if you grab any one point in here and you want to figure out what its corresponding value is over there, well, we got to add pi to it, right? So if this is a, whatever this point is, then this one's going to be a plus pi, right? The x coordinate, right? So like, meaning a is this, therefore this is a plus pi. Good, that's important. Or the other way around, if you want to go backwards, you subtract pi. So the reason I point that out is because we're working with 120 degrees, right? This guy is 120 degrees. So that means that you're over here. So if this was 0, that means that this guy right here is going to be 0 plus pi, which is pi, or 180 degrees. 120 is going to be somewhere around here. Does that make sense?
Yeah.
Good, good, good. Okay, so now I made this a little messy and I really need to be able to refer to it. So I'm going to make another one over here, like maybe a little less busy, just to get the stuff we need. So I'm copying the same kind of graph, but I'm just going to put in just the stuff we need. Okay, so we have this asymptote that comes this way, and we have tangent that kind of goes over here, like that, let's say, and then this thing comes over here like this and goes that way. Okay, 120 degrees is over here somewhere, and then that leads to some number, and that number is going to be something over here. Good. But then when we apply the tan inverse function, it isn't going to go backwards and give me that number. It's going to come over here and give me this number over here. Good. Sort of, kind of, maybe. Okay, so now let's go to our unit circle kind of description of things and see if we can figure things out a little bit better. So 120 degrees is over here. We need to figure out a one. Okay, so when is tangent going to be, so this is going to be tangent of 120 degrees, so here's 120 degrees, and so we're working with a reference value of 60 degrees. So if we drop our triangle, we end up with this, right? If we're on the unit circle. Should have drawn the circle first. Anyway. Okay, so we have a reference angle of 60 degrees in quadrant 2. Right, so then we have to go over to our standard triangle of 60 degrees. 60 degrees there, 30 degrees there, 1, root 3, and a 2. Okay, so what can we say? We go tangent of 60 degrees is equivalent to root 3 over 1. Okay, but in quadrant 1, right, in Q1. But now in quadrant 2, tangent is going to be rise over run, opposite over adjacent. And opposite is the y, which is going to be positive, but the x is negative. So tangent is negative in quadrant 2. Okay. Good. Okay, so tangent of 120 degrees then, which was equivalent to our original question, our original statement of tangent of 2 pi over 3. Is equal to tangent of 120 degrees, which is equal to -1 times tangent of 60 degrees, which is equivalent to -root 3. So far we're good. So we've managed to insert a -root 3 in here. Still all good? Still all good?
Yeah.
Good. Okay. But we can see from our graph that what we've done is we've established that this value right here is -root 3, right? This ordered pair is 120 degrees, comma, -root 3 on our graph here. But remember that they are pi apart. So when I want to go backwards, when I want to apply the tan inverse function, the tan inverse function is only applicable in the first period of pi that straddles the y-axis. Make this smaller and get the whole thing in there. Right? This central tan period here is the one that tan inverse is programmed to work with, because it's the function is 1 to 1 in that segment. So we started out at at 120 degrees, or 2 pi over 3. We plug it into our tangent function, and it gets us to this point right here, which is negative root 3. Okay? In degrees, we start at 120 degrees. We plug it into our tangent function. That's what this is. This is the tangent of theta function. Good. And so we get to here. But now, when we want to go backwards and plug it in the tan inverse function, it's not going to map me to that one. It's going to map me to this one. Good. And what is that one going to be? Well, that's this one minus, to go there, to go from this point to this point, subtract 180 degrees, or pi in radians. So just from that, I know this must be negative 60 degrees. Good? Kind of, sort of, maybe? Okay, and then the other thing that kind of complements that, the other way we know that, is because, so tangent inverse is only valid in Q1, right? That's positive 0 to pi over 2, or from 0 to 90 degrees, and in Q4, negative 0 to negative 90 degrees. 0 to negative 90 degrees is over here in Q4, right? An angle that goes negative goes in this direction, from 0, negative 1, negative 2, negative 3, all the way down to negative 90 degrees. So tangent inverse is only valid in one of these two places. Good. So where does there exist an angle that's going to result in negative root 3? Well, it's got to be down in quadrant 4. So sort of by that logic, we know that we have to have this angle over here. This is the one that works. Right? So this is an angle, tangent inverse of an angle, such that tangent of that angle equals to negative root 3. It's got to be in quadrant 4. Does that make sense? Maybe, kind of. Maybe.
Yeah, I can see inverse, right?
So here, let me put it all together then. So tangent inverse. So we have tangent inverse. Let me zoom out. Tangent inverse of tangent of 120 degrees. I'll do it in degrees first. Okay, this is tangent inverse of negative 1 times tangent of 60 degrees. Oh, sorry, tangent of 120 degrees. Oh, sorry, 60 degrees, like this. And then this was tangent inverse of negative root 3. Okay, but then when we apply this into tan inverse, we know we're going to get negative 60 degrees. So this was just writing it all in degrees. So if we started with that, that takes us to negative root 3. And negative root 3 takes us back to negative 60 degrees. In radians, so this original question was in radians, so we should stick to that. Tangent inverse of tangent of 2 pi over 3 is equivalent to tangent inverse of 60 degrees, which is pi over 3. Tangent of pi over 3 times negative 1. Which then gives you tangent inverse of negative 1 times root 3. And so this is going to give you negative pi over 3. Good, sort of, kind of questions So
negative 60 can be written in radians as negative pi over 3.
yes, negative 60 degrees is negative pi over 3 radians. Good.
Okay.
Okay, so the key to this, so this is a really hard question to get the subtleties. There's like these really subtle things that are happening, and it's kind of hard to see that, right? In the beginning of this section, we were really just doing things that were really straightforward, like sine inverse of sine of 30 degrees. Right, we started off with this. Okay, this takes you to some number, and then sine inverse, that brings you back to where you started. And so these two operations are inverse operations of each other. They undo each other. Cosine inverse of cosine of 30 degrees equals to 30 degrees. Whoa, what just happened? Why did you do that, program? Whoa. Anyway, so these two operations undo each other. And as long as we're in quadrant 1, everything works out really well. Go away. Tangent inverse of tangent of 30 degrees equals 30 degrees, right? These two operations undo each other. And everything works out really well. The problems start to happen when we get away from quadrant 1, and the sine inverse function might not give you the result you expect. Good? Because remember that the sine inverse, cosine inverse, tangent inverse functions have a restricted domain. They are only valid for a certain segment of the sine function. And if you, so you might get an unexpected result. So it's not as easy as just saying, just undo these or cancel these. You're not always going to get the exact same answer. So the key to this one was to recognize that the original value that they gave you, this one, is outside, it's not in the domain of the tangent inverse function. The tangent inverse function goes from negative 90 degrees to positive 90 degrees, and you're asking me about something in 120 degrees. It's not going to be in the original domain, so it's going to give you an unexpected answer. Good. We started at 120. Tangent of 120 is negative root 3. But now when you want to go backwards and plug negative root 3 into tangent inverse, it's not going to map you to 120 degrees. It's going to map you to negative 60 degrees. Right? So to wrap up this whole thing I did over here, we're saying that tangent inverse of tangent of 120 degrees equals negative 60 degrees. Right? They work out really well over here. Tangent inverse of tangent of 30 is 30. Cosine inverse of cosine of 30 is 30. Right? So as long as we're in quadrant 1, everything works out really well. But this one's not in quadrant 1, and it turns out to give you an unexpected result. Good. It's unexpected, but at the same time, well, initially unexpected, but once we know how it works, it becomes expected, and then we can work with it that way. So that if I really did want a positive angle, once I do this process, then I'd have to work with this to get the positive answers, right? Chapter 7, we're going to get into trigonometric equations, and that's when you really have to be aware what the tan inverse function results are, what kind of results you're going to get when you apply a tan inverse function, and then use that to find other angles that you might be interested in, right? Multiple solutions. Good? Sort of, kind of?
Yeah, I get it now. Thank you.
You're welcome. Let's confirm it with our calculator. Here. All right, let's go to degrees. Okay, I'm in degrees and quit. So let's try some stuff out. Like say, for example, I put in tangent of 55 degrees, I get some decimal, right? And then if I take sine inverse of that decimal, sine inverse of 0.81915, okay, to approximately, I should get 55 degrees. This little decimal is because I rounded, right? Okay, but basically it's a round trip. I start at 55 degrees, I plug it into the sine function, it gets me to this decimal, and then I plug that decimal back into the sine inverse function. They undo each other, and I get back to where I started. Okay, however, if I tried sine of, I don't know, 742 degrees, it gets me to some decimal. But if I type in sine inverse of that decimal, 0.3746, it's not going to know to bring me back to 742 degrees, right? The sine inverse function is limited. It can only give you answers between negative 90 and positive 90 degrees. So it gives me 21, almost 23 degrees, right? An angle between negative 90 to positive 90 degrees such that sine of that angle gives you the equivalent decimal. So note that sine of this, it's almost 22 degrees. Let's put 22 degrees in there. This one is going to be really close to that one. See how they're really, really close to each other? Well, in fact, they're the same ones up to this decimal approximation. So sine of 22 degrees and sine of 742 degrees are both giving me the same decimal output. So you just have to know that when you apply the sine inverse function, it's going to give you an angle between negative 90 and positive 90 degrees that is going to give you the same result as the one you're looking for. So you just have to be aware of that. Good. So in our case, tangent of 120 degrees, tangent of 120 degrees gave us that decimal. That's negative root 3 right there. Negative root 3. See, that's negative root 3. So tangent of 120 degrees is negative root 3. But now if you want to try and go backwards and type in negative 1.7320508008, okay, close enough. You get negative 60 degrees. Good? Good. Anybody have questions on any of this? Any more questions on this problem then? No? It's, you know, very subtle, and this is one of those problems that I think people, it's just so tempting, so easy to just use technology and find the answer. But it's there's a lot of subtlety here, and it really, really highlights understanding of what the tan inverse function is actually doing, the restriction of the domain. So there's a lot of good stuff here to really understand, right? To really understand why the answer is negative 60 degrees or negative pi over 3, you really got to understand the unit circle description of a tangent function, right? Opposite over adjacent on the unit circle. You got to understand our basic trigonometric triangles, right? So the reference angle was 60 degrees, so that's one that we can figure out without a calculator. You have to understand the fact that it's got a period of pi, and that's how you subtract pi to get to the previous value. So there's a lot of good stuff here. So make sure you really reach for the whole thing here and really understand the picture, the graph, the unit circle, the quadrants, why it's positive, why it's negative, this whole thing of finding an equivalent value, right? So 120 degrees, we referenced it to an angle in quadrant 1 that then again references a triangle that we know how to solve, that whose sides we know. Good. All right, so there's a lot of good stuff here, and we'll need it in chapter 7 as we move on. All right, so let's move on to chapter 7. And again, identities is another place where I think a lot of people just kind of rush to find the answer and are happy with that. I know that many of you have been mistreated by prior math instructors that somehow teach you that finding answers is important. And it kind of is, but it's just not that important, right? Math isn't about finding answers. I already knew the answer was negative 60 degrees. I don't need to give you a test for you to tell me the answer is negative 60 degrees. And it's really easy to use technology to just punch it in and it gives you the answer. Soon, I'm sure, I don't know if, well, are you guys aware of some math apps out there where you can take pictures of math problems and it just gives you the answer? There's one called Photo Math, I think it's called. Like, it's just a free app, and you can just write down a math problem, and you take a picture of it, and then it just and it gives you the answer. So I think initially it was just limited to algebra questions, you know, solve for x kind of deal. But I'm sure as we continue to develop our technology, it'll get more and more sophisticated, and eventually, you know, you'll just be able to take a picture of just about any math problem, and it'll just give you the answer, right? So we study math to get answers. Sure, that's kind of important, I guess, but really, math is just a tool to do brain push-ups. That's all it is. You're just doing brain exercises, building your ability to be inductive and deductive reasoning, to do inductive and deductive reasoning, and a whole lot of other great things, right? It teaches you to be meticulous and detail-oriented, and just a lot of good stuff that will eventually be helpful and useful in other areas, right? But using technology to find answers and being happy with that is kind of like turning on a treadmill at the gym and then standing on the little edge and be like, oh, I found a trick, and just stand on the edge, and the little thing will just roll, and then I can pretend that I ran, you know, whatever, a mile or 2 miles. It's like, why are you cheating the treadmill? What's the point? Right? Okay, so anyway, keeping in mind, these are little brain exercises. You're supposed to think through them, right? Don't get caught up on just find the answer and move on. Any rate, so back to identities. Identities is another place I think that people are just too busy, too much in a hurry to find the answer without really paying attention to the subtleties of what an identity is. So an identity, we're going to work with simplifying trigonometric expressions, proving trigonometric identities. This is the beginning of chapter 7, 7.1. Okay, so first, the difference between an equation and an identity, right? So we know that an equation is a statement that two mathematical expressions are equal, right? So here are some equations. X plus 2 equals to 5. That's an equation. Here is another statement here. This one has x plus 1 squared equals x squared plus 2x plus 1. And sine squared t plus cosine squared t equals to 1. Right, so the first one is an equation, and the others are identities. Right, so why are they identities? So an identity is an equation that is true for all the values. Right, so it doesn't matter what choice of x you select; it's always going to be true. So that's why in this case, this is true if and only if x equals to 3, right? We have to make a very special choice for x, and then it's true, right? That's the only time it's true. True if and only if x equals to 3. However, if I told you the statement 3x equals 2x plus x, that's always true. It doesn't even matter what you choose for x, always true. Right? Always true. Always true. And that's what an identity is. An identity is something that's always true. It doesn't matter what you choose for x. You could choose 1, you could choose -10, it doesn't matter. right? So it's different when we're working with an equation, we want to solve it. We want to find the values that make it a true statement. That's what's called solving the equation. With an identity, we don't want to solve it. There's no such thing as solving it. You know, if I gave you this and I told you solve it, what's the solve it? X could be anything, right? So in identities, we don't solve them. We want to just show that they're identities. We want to prove to ourselves and, well, in this case to me on a test, that the statement in front of you is not an equation, that it's in fact an identity. It's always true. Okay, and so that's what this this section will focus on. How do you do that? How do you show that something is an identity? There's a couple of techniques we'll be working with. So far, any questions on the distinction between an equation and an identity? An identity? Right, so sine squared t plus cosine squared t equals to 1. That's always true regardless of the choice of t. And that extends from this. So remember that on the unit circle, here's the unit circle, and we have this and we have that, and we create a triangle. It doesn't matter where you form your triangle, right? Anywhere on here. Let's say we form it down here, like this. So we have a point there. So then if this is some point A comma B, that means that this part here is A and this part there is B, like this. Right? Remember back when we worked on this unit, the unit circle in chapter 5, we established that this part here would be the cosine of the angle. So let's say that this is angle theta. Right? So this would be cosine of theta. And this one would be sine of theta. Good. And then this is the unit circle, so that means that this distance right here, the radius is 1. Okay, so this extends from a squared plus b squared equals to 1 squared, where this is cosine squared theta plus sine squared theta equals to 1. So Pythagorean theorem is always true for any value of a, b, and, well, in this case, the hypotenuse is always 1. So this is always true. Man, I don't know how the zoom button keeps getting hit. It's really getting annoying. Okay. So, again, any questions on the distinction between an equation and an identity? No. Okay, so certain identities are just going to be given to us. We're not going to spend a whole lot of time proving these. You're not responsible at this point in your math careers for the formal proofs of some of these things. Some of them are very easy to prove, and some of them are really hard to prove. And some of them are easy to prove by picture. So, you know, we've worked with these. Cosecant of x is equal to 1 over sine. Secant of x is equal to 1 over cosine. Cotangent of x is 1 over tangent. So these reciprocal identities, I think, are familiar by now. This one, we just talked about why it's true. It's always true. And then these two we can get by a simple algebraic manipulation here. So, for example, we could take sine squared theta plus cosine squared theta equals to 1. And then I could choose to divide this side by cosine squared theta, cosine squared theta, 1 over cosine squared theta, and then that gives me a 1 there. And sine over cosine is tangent, so that's how we get this next one. Tangent squared theta plus 1 equals to secant squared theta. Right, so that's how we get this one. And then we can do the same thing by dividing by sine squared instead of cosine squared, and that's how we'll get this one. This we already knew back when we were looking at the graphs. Sine of negative x is equal to negative sine of x. That's because we know that the sine function is odd. The cosine function is even. Remember that these are reflections. This is a reflection about the y-axis is equal to a reflection about the x-axis. So we can graphically prove those. I think we already did that back in chapter 5, I think. And then again, the proof of these, some of them are not so bad. Maybe looking at its graph. Let's look at the graph of the first one, for example. Sine of pi over 2 minus x equals to cosine of x. And let's do proof by picture. Let's graph these on Desmos and confirm that we think these two things are equal to each other. So I'm going to rewrite it this way. 90 degrees minus x equals to cosine of x. Okay, and then I'm going to just flip these around and say that this is sine of negative 90 degrees. Oops, sorry, negative x. Come on. Negative x plus 90 degrees equals to cosine of x. Good. And then remember that if we factor out this, we end up with this negative 1 here. It's negative 1 times x minus 90 degrees cosine of x. Okay, so remember that if we multiply the argument of the function by a negative, it's a reflection about the y-axis. So this is the sine function reflected about the y-axis and then shifted to the right by 90 degrees, and that is actually equal to the cosine function. Good. So pictorially, here we have just a rough sketch, and then we'll use Desmos. Here is the sine function. It'll go like that, sine of x. And then a reflection about the y-axis means that this will end up being this way, like this. Right, this is a reflection about the y-axis. And then if we shift it by 90 degrees to the right, then this guy here is 90 degrees. Right here is 180, negative 180. Here's positive 180. And then this guy was 90. So this is negative 90. So if we shift that way, then this thing comes like this. Right, it's been shifted that way by 90 degrees. But then remember that I'm just looking at a little piece of this. This thing really continues that way. This thing really continues that way. So then this thing really continues this way and comes that way and continues this way and comes that way. So this continues this way and comes that way. And oh wait, doesn't that look like the cosine function? So at this point, when I shifted it that way, we've arrived at our final statement that I wanted to make, right? That sine of negative x minus 90 degrees is really equal to cosine of x. Questions? Maybe I should have made it a little bit nicer. Any questions about that? Did that make sense? Y, here's x, right? So we have one period of sine, but really it continues. And then it's been shifted or reflected about the y-axis. It means it gets flipped about the y-axis, a mirror image about it. So this point comes over here to become here. And so we end up with this as one little image of sine. Then of course it continues. It goes that way and comes this way. And then it gets shifted to the right by 90 degrees. So this becomes positive 90 degrees. 0 and negative 90 degrees. Any questions? All right, let's look at Desmos with that. Same thing, just better pictures. Desmos, graphing calculator. Okay, so y equals to sine of x. So here is one period of the sine function. Okay, and then when we reflect it, y equals to sine of negative x. It's going to be a reflection about the y-axis. So this point right here went over there, right? And so this right here is one period of sine. This right here is that same period, the first period of pi reflected about the y-axis. Okay, so now we have that guy. And now if we shift it, y equals to sine of -1 parentheses x minus b, where b is going to be a little slider, and I want it to go from 0 to 90. Let's go to 0 to 120 by 5s. Okay, so when it's -0, then we have the exact same graph. When it's -5 degrees, it got shifted. Whoops, what did I do wrong here? Oh, it's because of this minus. Oh man, did I mess this up? Shifted to the... shifts it in the other direction, so it's got to be -90 degrees. Shifted to the right. Because the minus changes in the other direction. Minus. It's off. What did I do wrong? Oh, we're in radians here. Duh. Okay. Sorry. Now let's change this to radians. I'm sorry. Let's change it to degrees, and then we'll change this whole thing over here. Okay. So the x-axis, let's go from -100 degrees to positive 360 degrees, -1 to +1. That's too big. Make it 1.5. Make it 2. -2 to +2. Okay, now it's moving in the right. Or now it's making more sense. A little more sense. B. Now we're in the ballpark, because otherwise we were. Okay, anyway, so shifts it to the right. Here we are. It shifts it to the right by 90 degrees. So here's when b equals to 90, the green one. Right, so maybe I should zoom out a little more. Here we go. Okay, so starting from scratch here. Here's the sine function, one period of the sine function from 0 to 360 degrees. Right? And then we do a reflection, and the reflection is going to move it this way. So that same sine period is over here, right? Reflected about the y-axis. And now we want to take this guy and scoot it to the right. Here it is if we scoot it by 10 degrees, 15 degrees, 20 degrees, 35, 40 degrees, 55 degrees. And eventually when we get to 90 degrees, this one now looks exactly like a cosine function, right? So, oops, 90 degrees. Now this one looks exactly like a cosine function. So graphically, at least, hopefully we've proven that all of this manipulation, sine of -1 times x minus 90, right? This is when that's 90, is equivalent to just saying cosine x. So there you go, proof by picture. Does that make sense? Any questions, questions? No. And of course, if we kept going with the b value, right, eventually I can slide it so much that it, goes back to looking like a sine function, or it goes back to looking like another cosine function, depending on the value of b, right? I could keep going with that slide, and eventually it would get to a point where, again, it would look exactly like the original one, or it could look like a sine function from zero, starting at 0. Good. Okay, so you can do that kind of thing for several of these identities. So we're not going to spend too much time on those. That's about all the time I'm spending on this one. So there's other ones you can do. Spend some time playing around with these and confirm for yourself that it makes sense that these are identities, one side equals to the other. But for now, let's get back to the work we have to do. Okay. So identities. How do you prove that they're identities? We're going to be given a statement. You're going to work on the statement, and you want to get to a point where it is clearly obvious that what you have in front of you is an identity. There's a couple of methods we're going to look at. Identities enable us to write the same expression in different ways. It is often possible to rewrite a complicated looking expression as a much simpler one. So that's one idea. We have to find a way to reduce it from a complicated statement to something a little bit simpler. To simplify algebraic expressions, we use factoring or common denominators or special product formulas. And to simplify trigonometric expressions, we use these same techniques together with fundamental trigonometric identities. Okay, so first of all, this is not an identity because there is no equal sign here, right? This is just an expression. This is just a statement given. And I just want you to simplify. One technique is going to be to convert everything into your sines and cosines, right? And then often that simplifies. So how to simplify this? All we'd have to do is point out that cosine of t plus tangent of t times sine of t, that is equal to cosine of t plus, now by definition, tangent of t is sine of t over cosine of t times sine of t. Good. At which point, once you've done this whole conversion into sines, cosines, there's nothing but sines and cosines. One common shortcut that I like to use is just to go back to use s and c, because otherwise it looks really messy. This one's not that bad, but you'll see that when you do your homework, some of these get really, really messy, and sometimes it gets a little hard to see what you're doing just because there's so much writing going on. So I would recommend that you do this as part of your work to simplify things, right? So it's equal to this. So now how do we simplify this? Well, clearly we need a common denominator. This is going to be equal to c over 1 plus s squared over c. And then we multiply this side by c over c, and we'll end up with c squared over c plus s squared over c, which gives me c squared plus s squared over c. And we know that cosine squared theta plus sine squared theta is equal to 1. That's one of our identities. So we can reduce this to just be a 1. And so this just becomes 1 over c, which is 1 over cosine of theta, which is equal to secant of theta. Any questions? I'm going to put it all in one spot here. Any questions, any questions, any questions? No, no, no? Okay, I'm pretty sure that's what the author did. Sine over cosine, yep. Okay, and then common denominator turns into cosine squared t plus sine squared t over cosine of t. That turns into 1 over cosine, which is secant t. Oops, how did I get a theta in here? course I have it. Sorry. The angle variable is t, not theta. So if you're wondering where that theta came from, it's cosine of t and secant t. Okay, no questions? No. Okay, so that's the first trick here. Converting things to sine and cosine often helps you reduce an expression. Okay, but that was not an identity, right? That was just an expression. An identity has to have an equal sign. It's a type of equation. It's an equation where it doesn't matter what the input is. It's always going to be true that the left side equals the right-hand side. Okay, so many identities follow the fundamental from the fundamental identities. In the next example that follows, we learn how to prove that a given trigonometric equation is an identity, and in the process, we will see how to discover new identities. Okay, so one common issue. Okay, so here we have an equation. Again, we have an equation because this is sometimes true. For specific values of x is true. So there exists a solution to this, a place where the input makes it true. But it's also very easy to find a place where it's not true. So if you wanted to show this was not an identity, all you'd have to do is find a place where it's not true. So what the author is pointing out here is that for some choices of x is true, right? What's a really easy choice where it's true? Remember, x is an angle. So for example, at 0 degrees, sine of 0 degrees is 0, cosine of 0 degrees is 1. So it's true when x equals 0, right? Sine of 0 plus cosine of 0 degrees. This is going to be 0, and this is going to be 1. So we end up with 0 plus 1, and that equals to 1. So it's true. Good. But note that it's not true when x equals to pi over 4. Pi over 4, that's going to be root 2 over 2. That's 45 degrees. Right? Remember, that's one of our standard triangles. This is 90 degrees, which is pi over 4. Pi over 4. And this is 1 root 2. So either way you slice it, we get 1 over root 2 plus 1 over root 2. You rationalize them, and you end up with root 2, which is definitely not 1. So proving that it's not an identity can be as easy as finding a counterexample. A place where, oh, look, it's not true for this particular value, therefore this is not an identity. Good. Good. Okay, we want to start with one side or the other side, and we want to transform the, either one or both sides down to a point where they equal each other. Okay? What you do not want to do is to do anything across the equal signs. Don't do that. Because otherwise you can prove things that aren't true. You might accidentally prove things that are not true. Right? I can prove, if I do that, I can prove to you that 3 equals to 2, right? It's a very easy proof. All I'd say is that, okay, well, you can do whatever operation you want to one side, you can do to the other, right? So how about if I multiply both sides by 0? Multiply by 0. Okay, so multiply this side by 0, multiply this side by 0, and so now we end up with 0 equals to 0. And then people go backwards and they go, okay, so if this is true, then it must be that this is true, which must mean that this is true, right? So that's not going to work, right? So we don't want to do that. So you don't want to do this thing. This is not an equation. We're not solving for x here. You cannot do anything to both sides of the equal sign. Instead, what we're going to do is pick one or both sides and manipulate them. Find another equivalent version of it. Reduce it, cancel it, find a common denominator, rationalize it. You can do lots of things. You just can't go across the equal sign. to cancel something on both sides or divide by both sides or anything like that, right? So that's rule number one of identities. Do not do something to both sides of the equal sign. Good? Okay, so I would recommend that you do a little bit of scratch work on the side to figure out how to do it, and then you come back and then you kind of do a presentation, like a formal presentation of the answer. And when you do that, you should, the formal presentation should start with one side of the identity and then give you true statements, true statements, true statements, you know, as you manipulate and change it and make it fit to the other side. Good? Questions, 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 questions? Okay, so here's some examples. Here's an example. Cosine times secant theta, cosine of theta times secant theta minus cosine of theta equals to sine theta squared, right? Prove that this is an identity. Verify algebraically that the equation is an identity. So first of all, if I can find a counterexample, if I can find an angle such that if I plug that angle into the left side, it does not equal the right-hand side, then I've proven that it's not an identity. But if you do find one angle that works, that doesn't prove that it's an identity. Right? Does that make sense? So if you pick one unique value of theta, maybe you've helped to confirm for yourself that it's worthy to keep moving forward, that it's not an obviously wrong thing, but that's not good enough in terms of proving it that it's true. Good? Okay, so what are we going to do? Let's pick one side. You can pick either side or you can pick both sides, but experience shows that it's easier to work with the most complicated side. You want to reduce, cancel, and somehow manipulate this side to make it look like that. That's your goal, okay? And I think you'll find that it's easier to destroy than it is to create. So it's easier to knock this down, cancel things down, and reduce and make it look like the simpler case, rather than create, which would be to start with the simpler side and make it look like this more complicated thing over here. Okay, so the first thing I would say is let's take advantage of the trick we just learned before, that often if you convert things to sine and cosine, things get a little easier. So I'm just going to convert this, right, and say that this is equal to cosine of theta times 1 over cosine of theta minus cosine of theta. Good. Then common denominator is cosine of theta, so let's put a 1 there, times, and I'm going to multiply this by cosine of theta over cosine of theta. That's weird. Cosine of theta. Okay, so I'll end up with cosine of theta, and then it'll be 1 minus cosine squared theta over cosine of theta, at which point these two cancel. Cosine of theta cancel. And I end up with 1 minus cosine theta squared, right? And note that this is equal to sine, right? So using cosine squared theta plus sine squared theta equals to 1, I can say that sine squared theta equals to 1 minus cosine squared theta. So using that identity, I can then conclude that this is sine squared theta. Done. A little box, put a slash to it. That's traditional in math. Shown that you're done. Okay, so we started with one side, manipulated it, reduced, canceled, common denominators. You can use any prior established identities to help you transform your statement into your expression from one to the other, right? So this is a question about transformation. You want to manipulate it and make it look like the other side. This is not a matter of solving for theta, right? You cannot multiply across both sides. You can't cancel across both sides. We don't want to find the square root of both sides. right? All those operations would be silly here, right? So don't do stuff like this. Cosine of theta, and then we have secant of theta minus cosine of theta equals to sine squared theta, right? Terrible idea. Do not take the square root of both sides. That has nothing to do with what we're doing here, okay? Do not divide both sides by cosine of theta. That doesn't make sense here either. Don't do that, okay? Questions, 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 questions? Okay. And then confirm graphically that the equation is an identity. Okay, well, you can just go on Desmos and type in this ugly thing, and then type in this thing, and just confirm that they both give you the same result. So I don't think that that's worth our time, but you're welcome to try and do that on your own, and I'm sure that there's a nice graph over here from the author. There. You graph each side of the equation. Okay, so you'll get this sort of a graph. Just go to Desmos, type that in, you'll get, you know, some sort of graph. And then type in the other one, sine squared, and then you'll see that they give you the same thing. So I'll task you with that to try and confirm that for yourself, that this side equals that side if we just graph them both. Okay, but no questions about the identity part? So far we're good? So far easy? Note what it would take to go backwards. If you had started with the right-hand side, then your job would have been to basically write this in reverse, starting at sine theta. Okay, maybe this would have been easy, right? If somebody decided to start in the other direction, nothing wrong with that. It's just harder, right? Because if we have this, you're like, okay, maybe they would have noticed that the very first step would have been to do this. Okay, that might have been not bad. But then the next step would have been to do this. Okay, well that's kind of hard to see why, right? It would have been hard to note that the next step is to do this, cosine of theta over cosine of theta. That's hard. And then next it would have been to distribute one of those in here and say that this is 1 minus cosine squared theta over cosine of theta times cosine of theta. And then to separate them and right to basically do this in reverse would have been harder to do it, right? It's harder to create. It's harder to start off with a simple statement and make it be complicated. It's very often the case that it's easier to start with the more complicated one and reduce it, cancel it, and make it fit the smaller, easier one. Now, sometimes we'll be given ones that are so hard that they're hard on both sides of the equal sign. In those cases, manipulate maybe both sides kind of separately on some scratch paper and get to a point where they both definitely equal each other, and then come back and do a formal presentation guided by your side work. We'll get to one of those in a bit. Okay, I think there was no more questions on this one, so I'll move on. How about okay, that's fine. Okay. Solving this one. Okay, so again, this one's kind of ugly. How do we change this into this? You know, it's hard to choose which side is the easy side or the simpler side, which one's the more complicated side. If I start with the right-hand side, I think the first thing I would do is convert things into sines and cosines. That seems like a good, useful thing to do. And then maybe once I convert everything into sines and cosines, right? This is 1 over cosine, this is sine over cosine. Maybe then it might help me reduce it and convert it to this side. Also, if I started with this side, you know, by noting 1 minus something, one popular thing that often works is to multiply by its conjugate. So that might be a useful thing. Or it might just work with both sides sort of at the same time, right? So let's see. So this isn't my actual formal proof. You know, this is sort of side work. Side work. Let's see. Let's start with this side. Cosine u over 1 minus sine u. I'm going to multiply numerator and denominator by 1 plus sine u. What does that give me? 1 plus sine u. Okay, so that's going to result in cosine u times 1 plus sine u all over 1 minus sine squared u. Right, multiplying those two, which then gives me cosine of u times 1 plus sine u divided by, and then this is going to be cosine squared u, right? Again, using the same identity that cosine squared plus sine squared equals 1. And then one of these cancels. Does that help me? Let's see, that cancels with that guy. So I'll end up with just cosine 1 plus sine u over cosine u. Oh, and then I accidentally got to that side. I thought I wasn't going to need to do that, but okay. That's fine. And sort of on the other side, if I had started on the other side, if I had started with secant of u plus tangent of u, then this would be 1 over cosine u plus sine u cosine u, which means it's 1 plus sine u over cosine u. See how this side equals that side? I manipulated the right-hand side and I got to this. I manipulated the left-hand side and I got to this. They equal each other. And so if I wanted to use this side work to create my formal proof, I can go in either direction now and follow this guide. So if I wanted to, I can start here. Oh, come on. Stop hitting the zoom. Okay. So if I wanted to, I could start here and then go this way. Come on. I can go this way and then this way and then work my way up backwards and get to this way and end there. Right? Come on. Or the other way around, I can start here and go this way, this way, this way, this way, and then zigzag my way up to there. Either way, I can start with one side and do a bunch of manipulations to get to the other side. Good. So this is not your formal proof. Now you got to go back and write it in a nice, neat way. Proof. We're going to start with cosine of, well, let's go backwards. Let's just practice that. Looking at my side work going backwards. Proof. I'm going to start with secant of u plus tangent of u equals, okay, and then looking at this, I know that it's going to be 1 over cosine of u plus sine of u over cosine of u. Good. I'm just kind of following my side work as a guide. And so next I want to combine them. So this is equal to 1 plus sine of u over cosine of u. Cosine of u. Good. Next, I want to introduce this thing. Looks like I want to multiply numerator and denominator by cosine of u to get this. So next I want to say that this is equal to 1 plus sine of u over cosine of u. And then you're like, well, let's multiply this thing by cosine u over cosine u. Again, I'm kind of following this guide backwards, and I know that I need u. all over cosine squared u. So I'm at this stage. Now I know I need to do this. I need to rewrite it as 1 minus sine squared u. This is equal to cosine of u, 1 plus sine u, all over 1 minus sine squared u. So now I'm at this stage. And now, in order to get to this stage, I need to factor this denominator into these two. So this would be cosine u, 1 plus sine u, all over 1 minus sine u, 1 plus sine u. And then these two cancel. And I'm left with this thing. Cosine u over 1 minus sine u. And cosine u, 1 minus sine u. Finished. All right, let me zoom out a little bit and see if we can capture the whole thing in one shot. Stop it. And we're done from here. Right, we started with this, and then this equals that, which equals this, which equals this, which equals this, which equals that, which equals that, which equals that, and that's the other side, right? So we started in this case on the right-hand side of our identity, and we did a bunch of statements that are true, and we ended up with our left-hand side. Right? So in math books, what happens is that they don't show you this little side work, they just go through a formal proof like this. And sometimes it seems almost magical, like, how did you know to introduce this? I know it's true, but how did you know to do that, right? And, well, they're often guided by these little side work things, where in the side work it makes it a little easier to see. Good? Good, good, good. Questions? So, I made a simple one way more complicated than it needed to be, because as we were doing our little side work, we almost finished answering it anyway, right? If you're wondering, why didn't I just take the extra little step here of separating these two, and then that equals the right-hand side, then that would be the other proof of this. But I was just pointing out that sometimes both sides of the equal sign will be so hard that you'll want to work on both of them concurrently until you get to a point where they both equal each other, and then you can use that as a guide for creating your formal proof. Any questions? No? No? So I'm pretty sure that the author probably went in this direction. Let's see what your author did. Yeah, see, they did the exact same thing. Left-hand side, cosine u, 1 minus sine u, so we start there. Multiply numerator and denominator by the conjugate. So that's often a nice trick to help you find things. Then we FOIL this out. We end up with this, difference of squares. Good. Rewrite 1 minus sine squared u by cosine squared u. One of the cosines cancel. We separate this as 1 over cosine u, sine u over cosine u, and that gives you secant u plus tangent u. Good. So we end up with the left-hand side equals the right-hand side. Okay, one more example. Here we definitely have a case where the left-hand side is complicated, the right-hand side is complicated. Let's do some side work to both sides. We'll work on both sides at the same time, and then we'll use that as our guide to create our formal proof. Okay, so this is going to be 1 plus cosine theta over cosine theta, right? And maybe at the same time I want to work on the other hand, on the other side, tangent squared theta over secant theta minus 1, right? And I put the wiggly line to make sure that you don't accidentally do something with both sides of the equal sign or something, right? We don't want to do that. Okay, so maybe the first thing I'm thinking of, it seems pretty obvious, maybe might be useful to separate this as 1 over cosine theta plus cosine theta over cosine theta. I don't know, does that help? We have 1 over cosine theta plus 1. I'm not sure if that's helpful, but we ended up with secant theta plus 1. See where that leads me. What about this side? What can I do here? That's pretty ugly. How about if I begin by converting everything into sines and cosines? So this would be sine theta squared over cosine squared theta. That's the tangent part. That's tangent squared theta. Secant of theta is 1 over cosine of theta minus 1. Okay, common denominator here is going to be cosine, so let's get that going. Times cosine theta over cosine theta. Okay, so that's going to be giant fraction where we have this sine squared theta over cosine squared theta, and then we end up with 1 minus cosine of theta over cosine of theta. Okay. And what do we have when we have one giant fraction with a fraction in the numerator, a fraction in the denominator? We can multiply the numerator times the reciprocal of the denominator. So we end up with sine squared theta over cosine squared theta times cosine of theta over 1 minus cosine of theta. And this cancels. One of those cancels with that. And then I end up with sine of theta sine squared theta over cosine of theta 1 minus cosine of theta. Okay, what else can I do here? Keeping in mind, kind of keeping an eye on the other side, what I want it to look like. I can convert it into 1 minus cosine squared. So I can convert this into, this guy goes into 1 minus cosine squared theta. And then this turns into plus and minus cosine. And that should do it for us. Okay, so then that turns into 1 minus cosine squared theta over cosine of theta 1 minus cosine of theta. And then 1 minus cosine of theta can be factored into 1 plus cosine of theta times 1 minus cosine of theta. Come on. There. Good. So now this will cancel with that. And we're left with just 1 plus cosine of theta over cosine of theta, which equals to this. Oh, actually, that's... Well, this was not a very good example to show how you can manipulate both sides, since manipulating the right-hand side led me exactly to the left-hand side. So it looks like this is just the way to get to your answer. Oops. Good, since that's our answer. 1 plus cosine of theta over cosine of theta Yep, that's this side. So I started off doing side work, but then I accidentally found the right answer by just working on one side. So really you just want to rewrite this as your formal proof. Good. Okay, so proof, and it's this. I just need to start off with the formal sort of writing of it. Left hand side, starting on my left hand side, that equals to tangent squared theta over secant of theta minus 1. Good. And then, okay, so then you can do all these things, right? So tangent of theta is equal to sine of theta cosine of theta. It's equal to sine squared theta sine squared theta over cosine squared theta divided by, and then this thing, 1 over cosine of theta minus 1. And then guided again by this over here. It's really the same thing. So repeat all of that over here. All of that over here. And then eventually we get down to, as we saw over here, all these steps later, we end up with 1 plus cosine of theta divided by cosine of theta, and then that equals the right hand side. So you'd be done with your proof. Any questions? Any questions? None? None. Let's see what your author did. Left hand side, they separated into that. Right hand side. Oh, look at that. There's an easier way to do it. That's what's great about these things. There's always more than one way to do it. They use the tangent squared identity, of course, and then that simplifies much easier. Yes. Right, so using, let's go back up here. I want to use this identity here. Using tangent squared theta plus 1 equals to secant squared. Using this identity, we could have just made life a whole lot easier. Tangent squared plus 1 secant squared. Okay, let's go back to it. Okay, so tangent squared. So we can use tangent squared plus 1 equals to secant squared, and then it would have made life a little easier. Not that this proof is wrong, it's just longer than the other one, right? So there's just different ways to show that something is true. So let's redo this one and implement that identity. So tangent squared theta plus 1 equals to secant squared theta, right? Knowing that, that means that tangent squared theta equals to secant squared theta minus 1. Good. Okay, so now if we start off with tangent squared theta, so on the right-hand side of our statement, we had tangent squared theta divided by secant theta minus 1. Then on the right hand side, then we get to implement this identity for the numerator, and we end up with secant squared theta minus 1 over secant theta minus 1. So then we can convert this, we can factor this, since this is a difference of squares. We can factor it into secant theta minus 1 and secant theta plus 1. Secant theta plus 1. Good. And now this cancels with this one. This one cancels with that one. So on the right-hand side, we just end up with secant theta plus 1. And then on the left-hand side, we had cosine of theta over 1 plus cosine of theta. Oh, cosine of theta, 1 plus cosine of theta. 1 plus cosine of theta divided by cosine of theta was the left-hand side, so we can simplify this to be 1 over cosine of theta plus cosine of theta over cosine of theta. That gives you a 1, and this gives you secant of theta plus 1 on the left-hand side. So we can see how this then is equivalent to this, and we can see our path toward our proof. Right, so having this as side work allows me to formalize another nice proof for this. Proof, and let me repeat it again at this point. Proof that 1 plus cosine of theta over cosine of theta equals to tangent squared theta over secant theta minus 1. Okay, so proof of that, prove this is true. Okay, so then here's our formal proof. We're going to start on one side. How about this side? Tangent squared theta over secant theta minus 1. Okay, so then this is equal to secant squared theta minus 1 over secant theta minus 1, which is equal to secant theta plus 1 times secant theta minus 1 over secant theta minus 1. Good. So now this left-hand side, this cancels with this, which then just gives you secant theta plus 1. And then that means that this is 1 over cosine of theta plus 1, which means that this is 1 over cosine of theta plus cosine of theta over cosine of theta, which gives you 1 plus cosine of theta over cosine of theta, and that's the other side. 1 plus cosine of theta over cosine of theta, you're done. Right? When you're done, a little box, a little slash through it. Good? All right, any questions? Any questions at all? Any questions at all? No. Okay, trigonometric substitutions. So you might be asked to make a trigonometric substitution and simplify. So here's an example of something like that. Substitute sine of theta for x in the expression square root of 1 minus x squared and simplify. Assume that theta is an angle between 0 and pi over 2 radians or between 0 and 90 degrees. So we're in quadrant 1. Right? That's what they're saying here. So this is 0 is less than theta less than 90 degrees. Right? So this is quadrant 1. It's good. Things play well in quadrant 1. The signs are positive. The outputs of a sine are positive. The outputs of a cosine are positive. So everything works out really well. Okay, so then all you have to do is this. We have 1 minus x squared. And they told us to replace x with a sign. So we'd end up with 1 minus sine of theta squared. Notice, by the way, that this notation is the exact same notation as this. I've noticed some people get confused about that. But you have to be careful between this and this and this. Right? This one and this one are the same. But this one, you have to be careful because they really could mean that you want to square the theta first. And then, what the heck just happened? Some menu option keeps popping up. I don't even know what the heck it is. At any rate, so this one means this. Any rate, okay, so 1 minus sine squared, as we've used many times by now, is the same as sine squared theta, or we want to use this identity, sine squared theta, cosine squared theta equals to 1. So that means that this is going to be 1 minus cosine squared theta. This is going to be equal to cosine squared theta, not 1 minus. Cosine squared theta. And so the whole thing just equals to cosine of theta. And notice that this is going to be okay because the output of a cosine of theta in quadrant 1, and so note in quadrant 1, right, theta is trapped between 0 and pi over 2. Cosine of theta is positive. And so it'll match the original statement because the output of a root statement, right, the result of taking the square root of something is going to be positive. So they equal each other. Does that make sense? Kind of, maybe? Kind of, maybe? What would have happened if they told me for sure that theta, let's say sort of note or consider, if they had said, no, theta is definitely bigger than pi over 2, less than pi, therefore it's in quadrant 2. How would that change things? Well, if theta is for sure in quadrant 2, I know that this answer is negative. Good? And the result of this has to be positive. The square root of, the square root of 9, the square root of 10, it's always positive. So therefore, I would have had to multiply this by a -1 to make the whole thing balance. Good. Answer would have been that the square root of 1 minus x squared equals to negative cosine of theta, if theta was in quadrant 2. Any questions? No? Okay, this is the end of 7.1 then. Let's take a little break. We'll come back, I don't know, a little bit past 10:05 or so, and we'll dive into 7.2. Okay, we finished 7.1. Let's get started on 7.2. More fun with trig identities. Addition and subtraction formulas. The addition and subtraction formulas, evaluating expressions involving inverse trig functions, and then expressions of the form a sine x plus b cosine x, right? So these are our objectives for this section. So the addition and subtraction formulas are as follows. Here they are. And so remember that S and T in this case are angles or lengths of a curvature of a unit circle in the case of a radian. Same thing. Okay, so let's show one of these is true. They're pretty ugly to show that they're true, so we don't want to do too many of them. They just take a while. and they're pretty tricky. So we'll do one of them, and then we'll just assume the rest are true. So you're not responsible for proving these. All the identities that are provided to you in the book in a box, in these blue boxes, are things that you just are allowed to use without having to prove. But it's good to be able to follow a proof, right? So if you can follow what I'm doing, that should be good enough. But don't let this scare you. I wouldn't ask you to prove this on a test. But if you can follow what I'm doing, then anything you're asked to do should be way easier by comparison. So the first thing I want to remind you of, we're going to use a couple of things a lot. So one of the things in proving this, so let's prove that the cosine of s plus t is equal to cosine of s cosine of t minus sine s sine t. Good. Now, personally, I don't like s and t. My s's look like 5s, and my t's look like plus symbols, especially with this cursor thing that keeps like hiccuping, and then it doesn't look so good. So I'm just going to change it to another letter, if that's okay. So cosine of, I guess x and y, but they're kind of played out. How about a and b? Is that a little better? Cosine of a plus b equals 2, okay? Cosine of a times cosine of b minus sine of a sine of b, right? Same thing. Okay, so a couple of things I'm going to remind you of. We're going to use that sine of any angle, theta squared, plus cosine squared of any angle equals to 1. It doesn't matter what that angle is, right? As long as they're the exact same angle, you're going to get, this statement is going to be true. It could be something like sine squared of theta plus alpha, right? Where this is just an addition of two angles, plus cosine squared of theta plus alpha. Well, that's still going to be 1, right? If that's true, then that's true. So I'm just pointing it out that whatever's in here, as long as this is the same angle, this guy right here is the same angle as whatever is in this guy, sine squared of the same angle plus sine squared of this angle, as long as these are the same angles, gives you 1. Good. Another thing I want to remind you of is the distance formula. We're going to use that. So remember that in a Cartesian coordinate plane, if we have one point over here and another point over here, just let's call this point 1. And just for the sake of numbers, let's say that this is 1 comma 5. Right, so this is 5 units there, this is 1 unit there. And then over here, let's say that this is 7 comma 2. So this is point number 2. Point 2. Okay, so then remember the distance formula. Distance between point P1 and P2. Okay, how do we find the distance between these 2 points? We're going to create a triangle. Right? This is the distance right there, right? Connecting them. So if we go this way and we go this way, we form a triangle, except that was supposed to be straight there. You get the point. Then this distance right here is going to be the subtraction of the x-coordinates. It's going to be 7 minus 1. Good. And then this distance right here is going to be the subtraction of the y-coordinates. It's going to be 5 minus 2. Oops. 5 minus 2. Good. And then we use Pythagorean theorem. 7 minus 2. Let's go back to black over here. Distance. So d squared is going to be equal to the 7 minus 1 minus 1 squared plus the 5 minus 2 squared. Good. Questions, 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 questions. And then you just take the square root of both sides. So d equals to 7 minus 1 squared plus 5 minus 2 squared. And then you just take the square root of that whole thing. And because we're looking for a positive answer, right? The distance between these 2 points has to be a positive answer. I ignore the minus, right? Because really technically it's supposed to be plus or minus the square root. Is everyone with me? Any questions, 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 questions? No? And then what if it was just an arbitrary selection? Instead of just putting these numbers in there, let's say we had just 0.1. I don't know. How about here is 0.1. It is x1 comma y1. Here's 0.1. And then, you know, here's another point over there, and it is x2 minus, not minus, x2 comma y2. That's 0.2. Right? So again, if we want to find the distance between these 2 points, we think about creating that line there, except straight. Let's do it straight. Like that. And then we create this triangle that connects these two. And we think about that distance there, and we think about that distance there, right? This is the difference of y's, y sub 2 minus y sub 1. And this is going to be the distance, going to be the change in x's, x sub 2 minus x sub 1, right? Since this guy over here extends to x sub 2 right there, and over here this is x sub 1, so subtracting the 2 is going to give us that distance, right? And this traces over here to y sub 2 over there, and then y sub 1 over here. So if we subtract those two, we get that distance. Okay, so similar formula to this. D squared is going to be equal to y sub 2 minus y sub 1 squared plus x sub 2 minus x sub 1 squared. And so D equals to y sub 2 minus y sub 1 squared plus x sub 2 minus x sub 1 squared, and then we take the square root of that whole thing. Good? Questions, 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 questions? No? No, 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 no. Okay, so now that we're armed with those two statements, let's go back to trying to prove what we want to prove here. And we want to do, let's do the cosine one. So cosine, so we have cosine of A plus B, that this is equal to cosine A cosine B plus, I always forget the forms of these, it's minus, right? Minus sine, yep, minus sine A sine B. Cosine this minus sine this. Okay. All right. So on the unit circle, I inserted this little guy here to have a nice, pretty unit circle. So then, if we break this up, putting in the rectangular coordinate system roughly like this. So we have our y-axis. Here's our x-axis. Okay. So if it's the unit circle. Unit circle, then remember that in radians, the distance of the arc, that length of the arc, is equivalent to the angle, right? That's the definition of a radian. So if I measure this to be, let's say I measure this little arc part here, take my ruler out, and it turns out to be 3.2 units, whatever that is, then that means that in radians, this angle here is 3.2 radians. Now, I know that doesn't make any sense because the whole circle is 2 pi's, which is 6.24. 6.24 is 6.28 is one complete lap around. So 3.14 goes all the way over here. So this doesn't make sense to say that that's 3 units. So let's change that. Let's say that if this is 0.25 units, then this in radians must be 0.25 radians. Good. It's just that we usually write in multiples of pi, like pi over 4, pi over 3, that kind of a thing. Okay, so let's say that this is radian angle. Get rid of this thing here. Okay, so let's say this is radian angle let's say this is radian angle B, which means that this is distance B. And let's say that over here, let's put it in a different color. Let's say over here, from there to there, this part over here is radian angle A. So therefore, from here to here, that distance must be A. Good. So therefore, it must be true that from here to here, let's put it in red, that must mean that from there all the way to there, that must be angle A plus B. Good. Good, good, good. Okay, so now what I'm going to do is I'm going to take this distance there and move it below the x-axis. So I'm going to take this exact same length there and come over here and go the same number of units this way, like this, and end up at another point over here. So let's say that this is minus A. Good. Okay, now in terms of lengths, you know, if I had to take my measuring tape and measure it from this point here to this point over there, I'd have to measure one length of B and then also one length of A. So if this arc right here should be the exact same arc as this one in blue that starts here and walks this way in this direction and gets to here. Right? The arc that includes this B and this A minus B, this B and then this distance down here should be the same. Does that make sense? They both have one distance of A. I know that the negative is there, but the negative is just indicating a direction. The distance should be the same. So, I want to say that another way of saying the exact same thing would be if I put this there and said that this angle here is exactly the same as this angle here. Right? It has a little b and an a, and this one has a b and an a. Right? This angle must be the same as this one. The red angle must be the same. The distance on it must be the same as the blue one. Right? So because they must be the same, then that means they're opposite. The segment of the unit circle that they subtend must be the same. Therefore, when we connect this point and this point, this line right here has to be the same distance as this line and this line. That's the geometry that we need in order to be able to do this one. That's supposed to be a straight line. Okay, so that was just a geometric argument. Hopefully you've all had geometry and all of that sounds reasonable, I hope. Let me make sure this thing is straight. Okay, so let's call this d sub 2, and let's call this d sub 1. Good. Questions, 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 questions? So we're saying that angle A plus angle B must be equal to angle B plus angle negative A. Therefore, from here, geometry, it must be true that distance D1 equals to distance D2. Did I convince you guys of that being true? Anybody have any questions about that? No? Kind of? Maybe? No? No? Okay, so now let's find these ordered pairs. This one's easy. This guy right here. That's just going to be 1, 0. No problem. Good. This one, well, remember that the x-coordinate, we're on the unit circle, the x-coordinate is the cosine. This is cosine of b, comma, sine of b. Right? This point right there. Now this one way over here, this one, is going to be cosine of a plus b, comma, sine of a plus b. Good. And this one is going to be cosine of negative a, comma, sine of negative a. Everyone with me? Should I have another cool color? It's another cool color. Purples? Strong purple. So we have this point over here, this guy. And then across the way we have this guy. And then this. And this. Let me pause that there because, okay, cosine of negative a, remember cosine is even, so this is just equal to cosine of a. And sine is odd, so this becomes negative 1 times sine of a, or just negative sine a. Any questions, any questions, any questions? No? Okay, so next we want to work with this. The distance, the chord D1 is equal to the chord D2, and we want to use this formula in order to find that distance. Remember, the formula is to subtract, the distance between 2 points is to subtract their y coordinates and square them, plus subtract their x coordinates and square them, or in either order, right? We can switch this around and do the x's first, square them, do the y's first, square them. And it doesn't matter which one is which. You can put y sub 1 minus y sub 2. It doesn't matter because you're going to square it, so either way you get the same result. Good? Okay, so now let's do that. Let's, oops. Thought I gave myself room here. That's no good. Okay. Okay. So let's squeeze in the definition of d1 and d2. So d1 is going to be the x coordinates subtracted. So it'll be cosine of a plus b minus cosine of b. Oops, sorry, of minus 1. Minus 1, right? Looking at d1, so it's going to be d1. It's going to be this x coordinate, and then d1 is this one, minus this x coordinate, parentheses squared, plus, and then the difference of the y coordinates, which is going to be this one minus this one. So it'll be sine of a plus b minus 0, parentheses squared, and then that whole thing gets square rooted, right? And that must be equal to d sub 2. Now d sub 2 is the blue ones. It's going to be the difference of the x coordinates. So it'll be cosine of b minus sine a, parentheses squared, plus the difference of the y coordinates, which is going to be sine b and then minus negative sine a. Sine b minus negative sine a squared. And then the square root of that whole thing. Any questions? Difference of the x coordinate squared, difference of the y coordinate squared, square root the whole thing, that's how you get it. Good? No questions. Okay, so now we're going to simplify this. First of all, we can square both sides, so that gets rid of the roots. And then we're going to FOIL this guy out, so we'll end up with cosine squared. Oh yeah, just to make sure. Let's square this side. Let's square that side. That gets rid of the roots. Okay, then we FOIL this, and we'll end up with cosine squared of a plus b minus twice cosine of a plus b plus 1. Minus 0 doesn't do anything, so we just really have plus a sine squared of a plus b equals, okay, FOIL this side, we end up with cosine squared b minus twice cosine b sine a plus sine squared a. That's how we FOIL that guy. And then this guy, I'll just put a plus, and we can rewrite sine b plus sine a, parentheses squared, and then I'll square it next, right below here. But notice that if I bring these two things together, cosine squared a plus b plus sine squared a plus b, just this one and this one, they're really just going to give me a 1, right? Minus 2. plus b plus 1. And then on the other hand, I end up with a 1 from here. So I have a 1. And then minus 2 cosine b cosine a plus 2 sine b sine a. And then these two gave me the other one. Right? This one and this one give you another plus 1. Okay, so I'm going to combine these two ones to give me a 2 minus 2 cosine of a plus b equals to 2 minus 2 cosine b cosine a plus 2 sine b sine a. Subtract 2 from both sides, minus 2, and we're almost there. Minus 2 cosine of a plus b equals to minus 2 cosine of b cosine of a plus 2 sine of b sine of a. Divide everything by negative 2. Negative 2, negative 2, and we arrive at our destination here. Cosine of a plus b is equal to cosine of b cosine of a minus sine of b sine of a. And usually these things are flipped around, so we can flip around them and multiply these, and switch them around. And then we get to cosine of a plus b equals to cosine of a cosine of b minus sine of a sine of b. That was fun. Any questions? Okay, so like I said before, don't let this intimidate you. I wouldn't ask you to prove this on a test or anything. It was just a way of proving one of those identities, just to show you that there is a way to prove it. You know, everything in math is presented for a reason, and sometimes that reason is too complicated for us to get there, but you have to trust that, you know, there is a reason. Okay. Any questions, any questions, any questions? So all that work was just to show that cosine of s plus t equals to cosine of s, cosine of t minus sine s, sine t. The others can be proved in similar manners, but we're definitely not going to go through those, and like I said, you're not responsible for that. You just have to know these properties, use them, love them, and move on. Okay? So what will you be asked to do? Your questions will be asked be similar to this, answering these kinds of things. Find the exact value of cosine of 75 degrees, or find the exact value of cosine of pi over 12. Good. Okay, so for the first one, part A, cosine of 75 degrees, well, we just have to know, we have to be clever enough to separate this into cosine of 45 degrees plus 30 degrees. 45 degrees, 30 degrees, they add up to 75 degrees. And we know things about 45 degrees, right? Back to our standard ones. Right, this is 45 degrees. And our other standard triangle, this is 60 degrees, this is 30 degrees. This is 1, root 3, and 2, right? Everything's stemming from a square where all the sides are 1, or an equilateral triangle where all the sides are 2. Okay, so we can get everything we want from these. And now we know that cosine of a plus b is equal to cosine of a times cosine of b minus sine of a sine of b. Good. Right? This is exactly what we just proved. Cosine of a plus b. Cosine of a plus b equals to cosine of a times cosine of b minus sine of a sine of b. Right? Which is this guy over here. Cosine of a plus b equals to cosine of a cosine of b minus sine of a sine of b. Okay, so we can just use that property to separate it this way. Cosine of 75 degrees is equal to this ugly thing. And now each one of these is just a simple result. Cosine of 45 degrees, that's root 2 over 2. Right, it's 1 over root 2, rationalized gives you this. And cosine of 30 degrees is root 3 over 2. Good. Minus sine of 45 degrees, that's root 2 over 2. Times sine of 30 degrees, which is equal to 1/2. Okay. So combining these, this gives you root 6 minus root 2 all over 2. And they did want the exact value, so that's good enough. Otherwise, we can get our calculator and approximate it. Otherwise, you can also factor out a root 2. I'm not really sure which one would be the best choice. We can factor out a root 2 from up here and end up with root 2, root 3 minus 1 all over 4. Oops. This is a 4 here, not a 2. Any questions? No. Let's check in on the author. What did he do? Root 6 minus root 2 over 4. Okay, now the other one gets a little trickier because we go to radians. Pi over 12. So cosine of pi over 12. Now, I'm not sure what that is. So the first thing I would do is convert it to degrees. It's easier to visualize things in degrees. So you just get that, and so you need to figure out 18 divided by 12, well, 180 divided by 12, and I think that's going to be 15. $180 divided by 12, 15, yay. Okay, so this is the same thing as asking you, what is cosine of 15 degrees? And in terms of our standard angles, then that's the same thing as cosine of 45 degrees minus 30 degrees. Right, that's 15 degrees. We can always go back to radians now, since now we know it's easier to work with it. That's pi over 4 minus, and that's pi over 6. Good. This step is not necessary. Okay, but now we need to figure out what's going on with this subtraction. We know the formula for plus. I didn't prove the formula for minus, and I'm not going to. So you're going to have to rely on your tables or memorize them to be able to find it. So when we have a subtraction of angles, it's cosine s, cosine t plus. Right? So with the cosine one, they're kind of opposite values here. Here we have a plus, here we have a minus. So a minus and a plus. Okay, so that means that this is going to be equal to cosine of pi over 4, cosine of pi over 6, plus sine of pi over 4, sine of pi over 6. Again, if you're having trouble with all the radian values, that's okay. You don't have to go to radians. You can stick to the degrees. You can say that this is cosine of 45 degrees times cosine of 30 degrees plus sine of 45 degrees sine of 30 degrees. Good. So this is still root 2 over 2 times cosine of 30 degrees is equal to 1/2. Cosine of What did I do? Cosine of 30 degrees is root 3 over 2. You guys aren't catching me on anything, any mistakes I make. Plus root 2 over 2 times 1/2. So it's going to be a very similar answer to before. We end up with root 6 plus root 2 over 4 is one way of writing it. Or if we factor out that root 2, we could say it's root 2 parentheses root 3 plus 1 divided by 4. Any questions? No questions, no questions, no questions, no questions. No, no, no. Okay, let's check in with the author. So, yep, pi over 4 minus pi over 6, which gives you this, true. So here's our formula for this, the difference of two angles. Cosine of the difference of two angles is equal to this. And then these are standard triangles. And so we get this. Good. Okay, next, prove that this is true. Well, that's going to be a pretty easy application. So to prove this, that's easy. Let's just start with the more complicated side. Cosine of pi over 2 minus u. Well, we just established that this is equal to cosine of pi over 2 cosine of u plus sine of pi over 2 sine of u. Good. Equals to cosine of pi over 2 is cosine of 90 degrees. This is a 0. So this is 0 times cosine of u plus sine of pi over 2 is a 1 sine of u. So this whole thing just becomes sine of u. So we started with the left-hand side and ended up with the right-hand side, so we've proved it. Right? Right-hand side and left-hand side. Any questions? This is 0. And then 1 times anything is just that value. No questions, no questions, no questions. No, 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 no. We're good? Okay, let's see what else they got. Okay, well, that's what the author did. Same thing. Oh, we can also prove the same thing with a nice little triangle. Right? If we have a right triangle and this is u, then its opposite side must be pi over 2 minus u, right? Because the sum of the internal angles must be equal to 180 degrees. So if this side is b, and this side is a, and this side is r, then cosine of, sine of u is b over r, b over r, okay, b over r. But at the same time, cosine of this must be b over r. So it must be true that cosine of pi over 2 minus u is equal to sine of u. Questions, questions, questions? So a nice geometric proof that this is true, that cosine of pi over 2 minus u is equal to sine of u. Or we can take advantage of that property, right, of our difference of angles, our subtraction formula for cosine. Okay, let's try this. Show that if f of x equals to sine of x, show that this is true. Okay, so let's see. Well, we begin by doing this. Here's our function, and we want to input this. So we have sine of x plus h minus sine of x all over h. And this is kind of silly. We're just going to use or take advantage of our addition formula for the sine function. And I believe that that's going to be sine of x cosine of h minus sine of x cosine of h. I don't have these memorized actually, so let's double check. The addition formula for sine. I have the worst memory ever. That's why I pick math. Sine, okay, so when there's an addition, sine of x plus a t, the addition, then is sine, cosine, cosine, sine. Yeah, sine, cosine, cosine, sine. Sine, cosine, well, it doesn't really matter. Well, okay, let's. So it's going to be sine of x and then cosine x sine h minus sine x all over h. Good. Questions, questions, questions? Good. Okay, so I'm going to bring together this one and factor out the sine. So I'll end up with sine of x cosine of h minus sine of x minus cosine x sine h all over h. And then if I factor out the sine x, we end up with sine x cosine of h minus 1 minus cosine x sine of h all over h. And then that's what they wanted. I know it looks ugly, but that's really the answer, since they wanted you to prove this. Cosine h minus 1 over h minus, let me make sure that's what they wanted. Cosine x, wait, why do I have a minus? Man, you guys are not stopping me with my mistakes. I blame you. This is a plus. The formula gives us a plus here. I don't know why I have a minus. No clue why I have a minus. Anyway, so this must be the plus, which means that this is the plus, which means that there's a plus there. Okay? And it was cosine of x, cosine x times sine of h over h. There's the whole thing. Any questions at all? No? No questions, no questions? Okay, which is exactly the same thing the author did, except without any mistakes. Sin x cosine h, cosine x sine h. Factor out the sine, and get the same answer. Evaluating expressions involving inverse trig functions. So write cosine inverse x, sine of cosine inverse x plus tan inverse y as an algebraic expression in x, where x and y, where x is between -1 and 1 and y is a real number. Okay, so what we want to do here is the following. We have sine of cosine inverse of x plus tangent inverse of y. Good. So remember that in the sine function, we input an angle, and then out will pop out a decimal, right? A number between -1 and 1. So the cosine inverse function works the other way around. We're inputting a decimal between -1 and 1, goes in there, and then out will pop out an angle. And same thing with the tan inverse function. Tan inverse function, it's tan inverse. We input a number. Now it's not bounded. The tan inverse function can be any real number, and out will pop out an angle. Good. So this is an angle. Good. So I'm going to say that this is some angle theta, and this is some angle phi. Alpha, sorry. Good. So I'm really asking to find sine of theta plus alpha, where theta equals to cosine inverse of x, and alpha equals tangent inverse of y. Okay, so by definition, theta equals cosine inverse of x if and only if it's true that cosine of theta equals x. And same thing over here, alpha equals tan inverse of y if and only if it's true that tangent of alpha equals y. Good. So now what we're going to do is create a little triangle, arbitrary triangle in space over here. And then arbitrarily we can just say that this is angle theta. And we can rewrite this as x over 1 and y over 1. Good. So cosine is adjacent over hypotenuse, so this could be x, this could be a 1. Good, 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 good. So therefore, let's erase all of this. Therefore, I can find the missing side. Missing side a. So remember that it must be true that a squared plus x squared equals 1. So a equals the square root of 1 minus x squared. And it's a distance, so we can ignore the minus. In quadrant 1, right? So we're arbitrarily thinking this in quadrant 1. So this is equal to root 1 minus x squared. And then same thing over here. Here's this arbitrary triangle. And then here is alpha. Tangent is opposite over adjacent, so that must be y over 1. And so there's this unknown distance over there, and so it must be that 1 squared plus y squared equals to b squared. So b equals to the square root of 1 plus y squared. Good. So we have these two triangles, and now we can use our formula for the addition. So here we can bring this down here. Now this is going to be equal to sine of theta cosine of alpha plus cosine of alpha, cosine of theta, come on, plus cosine of theta sine of alpha. Make sure I got that one right this time. Sine, cosine, and then cosine, sine. And a plus. Good. So this equals this, and then this equals this. And then each one of these parts we can get from our two established triangles. Sine of theta is opposite over hypotenuse. So that'll be equal to root 1 minus x squared over 1 times cosine of alpha. Alpha is 1 over that. So that'll be 1 over square root of 1 plus y squared plus cosine of theta, which is equal to 1 over, adjacent to hypotenuse would be x over 1 times sine of alpha, which is equal to y over that. Y over the square root of 1 plus y squared. Good. So we can bring them together. Luckily, they have the same denominator, being this. So it's going to be 1 minus x squared square rooted plus xy all over 1 plus y squared square root of that whole thing. Questions? Questions? Let's see what the author did for this one. Okay, so we have same triangles, theta, okay, x over 1, yep, same triangles. And then, same thing there. Yeah, same thing. You just stop there. Yeah, he just stopped there. Questions, 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 questions? No? We're good, we're good? Okay, so for all of these that involved something that looks like this, create triangles. Set up your cosine inverse, your sine inverse, your tangent inverse. Set them equal to some angle that's unknown, alpha or phi or theta, whatever. Create the triangle. Use Pythagorean's theorem to solve for the missing side. And then from that point on, you can find all the trigonometric functions based on that angle. Okay? Okay, we're almost done with section 7.2. There's one more concept, but I'm out of time, so this would be a good place to stop for today. So we'll pick up on this, expressing expressions of the form a sine x plus b cosine x tomorrow.